All right, so questions about anything coming up or anything from last class? Okay, so we are working on chapter 7 and 8, and last time we were here, we were talking about the orbitals. These are the f orbitals, d orbitals, p. We talked about our s, and way back up here, we talked about our blocks. So we're going to revisit those blocks today as we look at our electron configuration. And again, I'm hoping everybody will find time to go through the video. Oops. The video covers the beginnings of the lecture on electron configuration, orbital diagrams, and I will post the PowerPoint notes with my handwriting on them for those of you who would prefer to look over the notes rather than watch the videos. But the videos are super exciting. All right. So where we're starting out is with our irregular electron configuration. So we're going to start off with chromium right here. And I'm actually going to open up an extra page. And I'm going to start with chromium as if it was a regular configuration. So if chromium was a regular element. So chromium is not a regular element, it's irregular, but the first thing I want to do is review what it would look like if it was regular. All right, so we're going to start with our periodic table of the elements. So here what we're doing is we're going to walk through our periodic table. So before we do that, let's put our blocks down. So this is the S block. And last class I told you that helium truly belongs to that S block. All right, then this is the D block in here. All right, so that is our D block. And over here is our P block. And finally, we have our F block down here. All right, and the element we're looking at is chromium. So what we're going to do is walk ourselves through the periodic table until we get to chromium. So for those of you who haven't looked at the video and it's been a long time since electron configuration, the idea of electron configuration is that we want to know where every electron lives normally. This is its ground state before it became excited, before it jumped off, let off lights, and we all went, ooh, for the fireworks. This is where it should be. This is where it lives. And every electron has a place. It has an energy level and it has an orbital. And that orbital is the s, p, d, or f. All right, so let's talk about chromium now. So I'm going to walk through the periodic table, and I'm going to start with energy level 1. And we are in the S block, and we have two elements in the S block in the first energy level. Hydrogen is the first one, helium is the second one. They each give off an electron. So here I'm going to start off saying 1s2, where 1 is my energy level, S is the block, and 2 tells us that we have 2 electrons. And again, 1 will come from hydrogen, 1 comes from helium. So any questions so far about why we started with 1s2? All right, so next up, we are walking through our periodic table, and I'm coming right down here, and it is the second energy level. So I'm going to put a 2. We are still in the S block, so I'm going to call this 2s. And then I have 2 elements here. Each one gives off 1 electron, so I'm going to say 2s2 next. So again, 2s2, change my colors here. 2s2 comes from there we go. 2s2 right here comes from second energy level, S block, and 2 elements, each one giving off 1 electron. So any questions about the 1s2 or the 2s2 so far? All right, so let's keep moving on. Now I'm right over here. I am still in the second energy level, so I'm going to put another 2. But now I'm in the P block, so I'm going to say 2P. And if I look at the number of elements, 1, 2, 3, 4, 5, and 6, there are 6 elements. Each one gives off an electron. So here is 2p6. So far I have 1s2, 2s2, 2p6. So questions on anything? All right, so let's keep on moving. And next up, I want to talk about the electrons that come from sodium and magnesium. So what will I put next in this electron configuration? Let's start with the energy level. What is the energy level down here? All right, excellent. So I'm hearing a 3, and I'm also hearing an S. And it is, yes, 3, an S, and also a 2. So the 3 comes from the energy level. The S comes from the fact these 2 are in the S block. And then the 2 comes from the fact that we do have 2 of them. So 3s2. So any questions so far about 3s2? All right, so next up, we're moving on to these elements right over here. And what should we write for those elements? How do we represent those? All right, so I'm seeing some 3p6s, and those look excellent. So third energy level, we are in the P block. And there are 6 elements here, each one representing an electron. And that's where the 3p6 comes from. So any questions on anything here so far? All right, so let's keep on moving. And next up, we have these 2 elements here. How are we going to represent those 2 elements? Excellent. So I'm seeing some 4s2s coming through. Fabulous. So that is true. It is a 4s2. We are in the 4th energy level. We are in the S block, and there are 2 of these elements. All right, so any questions on anything so far? All right, so next up, we are moving into the Ds. And the Ds are where things can get a little tricky. Let's go with brown. All right, so now we're looking at these elements right here, and we're stopping at chromium, because chromium's the element we're truly interested in. In last class, we said that Ds do something interesting. In a D, we are going to have the row minus 1. So instead of using 4, even though we're in the 4th row, we have to say 3. So let's see if I can move this over. So I'm going to say 3 for the 3rd energy level, D for the D block, and now I'm going to count over 1, 2, 3, 4. And this would be the regular configuration for chromium if it was a regular element. I'm going to show you how to change it to make it an irregular element, which it is, but this is a regular configuration. Any questions on this chromium as a regular configuration? Good question, Andrew. Yes, so we're going to do that next. And what I'm going to say in a test or quiz is you're going to write it whichever way I ask you to. So if I say use the inert gas configuration, use the inert gas abbreviation, then you use that. If I say don't use it, then you don't use it. So this time I'm doing the full thing just because it's our first time doing it together. But in the future, you're right. If it's this far down on the periodic table, I will be using that inert core shortcut. All right, other questions so far? Okay, so let's go ahead and copy this down to the previous page. So this is if chromium was a regular element, which it is not, but we're going to pretend it is for a moment. And this is our electron. Configuration. And now Andrew brought up a really good point here. So a lot of times when you have an element that's further down on the periodic table, it gets a little tiresome to use all of this. And there is a shortcut. So let me talk about that shortcut. Okay, so here is our chromium, and the shortcut is using a noble gas as your core. So sometimes we call this a noble gas core, an inert gas core, or an inert abbreviation, a noble gas abbreviation. I'll be really clear on the test if I want you to use the abbreviation, and I'll also be really clear if I don't want you to use the abbreviation. And so I will guarantee you on your next test, you will have some of these electron configurations, and there will be at least one where I say do not use the inert core abbreviation, and there'll be at least one where I say please use the inert core abbreviation. So I want to see if you can do this both with and without that abbreviation. But let's find out how to do that abbreviation. So from chromium, we're going up, and we're going all the way to the end here. And argon is the closest noble gas that is before it. And you always have to use the gas that is before. You can never use the gas that is after. And it does always have to be one of the noble gases. You can never use any other element for this abbreviation. All right, so that said, I'm going to start off with argon. And then I just say what is after argon. So after argon, we have potassium and calcium, so that is 4s2. And then we go into our D block, and it looks like we have 1, 2, 3, 4 of those D elements. And this is going to be a 3d4. Remembering that the reason it's a 3 is because in the D block, you always do rho minus 1. So you always drop down 1 in the D block. So this is an abbreviation for the regular configuration for chromium. So any questions on this right here on how to use that inert core abbreviation? For those of you who are seeing this for the first time, please watch those videos. This will go into a lot of detail on how to use that abbreviation method. All right, so again, electron configuration. There are two methods of writing it. One is the full configuration, and one is the noble gas core, which you see below it. Now there's another way of talking about this, and this is called an orbital diagram. Also known as arrow notation. See a question coming in, would you want to see argon 18? Chris, what do you mean by the 18 for the argon? Are you asking if I would want you to specify 18 on there? Yes, so I do not ask you to specify that 18. That's not a typical part of the configuration. So I think you're looking at the 18 right over here, right? Yes, so I do not ask you to do that 18. If you wanted to, you can, but I wouldn't ask you to do that. Good question. All right, other questions so far? Okay, so orbital diagrams, also known as arrow notation. And when it's a regular paper test, people often get confused with the orbital diagram. They try to draw a picture. They try to draw me an S or a P. This is not either of those. It is our arrow notation. So let's talk about what it would look like for our chromium. Here's argon. And then once upon a time, way back last class, we said all S's have only one type, or we should say one S orbital. So I draw only one line for it. And we said there were 5 types of Ds. So we draw 5 lines, 1, 2, 3, 4, 5, for our Ds. Now, if this was a regular class and I was going to ask you to draw all this out, I would tell you make sure I can see the difference between your S's and your D's. So some people like to write their lines really close together. And then it's hard for me to tell where the S's stop and the D's begin. So what I would tell you is that you would need to make sure there's a gap there, or if you're worried that I won't recognize where you meant to stop one, you can always draw a line in there. So again, we always have one line for the S's because there's only one type of S orbital, and we always have 5 lines for the D's. Even if you're not going to fill in all of those D's, we still always have to do 5 lines anytime you're dealing with the D. All right, so up here we said there were 2 electrons in the S. So I'm going to draw an arrow to represent the electron. And since there's 2 electrons, I need to put 2 arrows in here. And whenever you have 2 electrons in the same orbital, you always have to have one, which we call spin up, and the other spin down. We represent that with an arrow up and an arrow down. What's truly happening is these electrons are spinning, and one needs to spin clockwise, the other counterclockwise. When they do that, they're canceling out each other's magnetism. Now, if they didn't do that, let's say they all spun kind of in unison in the same direction. Let's imagine by the time we get down to, I don't know, nobelium, 102, you have 102 electrons all spinning together. When that happens, you would have massive magnetism, and we don't want that. So instead, whenever you get 2 electrons together in the same orbital, they have to cancel out each other's spin. So I think of it as spin up and spin down, but again, in truth, it means one spins clockwise while the other counterclockwise. I'm getting my fingers going here. So they got to spin opposite to cancel out the magnetism. All right, so that is our 4s. Now we have the 4 electrons in the 3d to put in. Now our rule for putting in electrons is that every orbital gets 1 electron before anybody gets 2. So I think of it as a buffet. Nobody gets to eat twice before everybody gets to eat once. So here I'm going to say 1, 2, 3, and 4, and then I run out of electrons. So notice we cannot double up one while you have some that are sitting empty. You're not allowed to do that. The real reason you can't do that is there is something we call electron-electron repulsion. You have 2 negative particles. When you put them close to each other, it actually raises the energy of the atom because you're pushing 2 negative things close to each other, and again, they repel each other. Now, if they have to, they will tolerate it. But if they do not have to, if there is an equal energy orbital, and we officially call these degenerate, not because we're really mad at them and we know its mother used to call it degenerate and we're trying to invoke those bad childhood memories, but the word degenerate just means equal in energy. So if these are all equal in energy, there's no reason to double up these electrons, which creates a high energy, unstable environment, when we could spread them out. So again, our rule, and the way I like to remember it, is think of it like a buffet. Every orbital gets an electron before anybody gets 2. All right, so we're still talking about the regular configuration, and next I'm going to show you how it becomes irregular. But any questions on what we've done so far? So again, I'm hoping that everything we're doing here is a review for you, and if it's not, please watch those videos. Also remember, during the lab period, after lab, we can talk more about this or any other chemistry-related thing. No good to you for biology or physics. Okay, so all of this was if it was a regular element. But the fact is, chromium is not regular. Chromium dances to the beat of its own drummer, and I want to show you why. All right, so I'm going to take its orbital diagram, and we're going to modify it a little bit. All right, so if this was true for chromium, and I mentioned that these orbitals right here, they're all equal in energy. There is no reason that one electron needs to be, say, right here, and it can't be over here. And likewise, there's no reason this electron needs to be here instead of over there. That's all equal energy. There's no energetic reason, it's not energetically favorable for an electron to be in one orbital over the other as long as they're equal in energy. Well, that actually causes a problem for the element because they do not pick an orbital and stay there now. Now they start jumping around and everything's moving. And the way I think of this, let's say you are driving the carpool and you're driving the minivan down the freeway and the kids in the back are all moving from seat to seat. So let's say this little kid here is like, ew, I'm not sitting next to that one. I'm going to jump over here. And the other one is like, no way, I'm not sitting next to that electron, and starts jumping over here. So it is a similar situation, just like you would find that very destabilizing as you're trying to drive down the freeway. The atom is finding it very destabilizing. And for the atom, when it is destabilized, that means it has increased energy. And the atoms are always going to do anything they can to lower their energy level. Just like you're driving that minivan and your energy is going up, you're starting to get angry, you're getting a little red in the face, and you're yelling back there, hey, stay put, keep your seatbelt on. And they're like, haha, we can move as much as we want. There's no energy cost, so why wouldn't we move around? And so the atom is going to do exactly what you would do if you have an adult in the front seat and you say, hey, I'm going to pull this minivan over and someone's going to come back and sit with you to make sure everybody behaves themselves. So suddenly, one of these electrons, which I think of as your front seat adult, is going to move back here. And we call that a promotion. So it's actually getting promoted to the back seat. And it is going to be there to stabilize these electrons so they can't move around and destabilize the element anymore. So what we call the irregular configuration for chromium, it's going to look something like so. We're going to have our argon. We have our 4s and our 3ds. We have our original electron that's sitting in that 4s. And we have our 4 original electrons in the 3d. But now you have a new electron in the 3ds. This one used to live, and let me go ahead and color this one in purple so we know which one moved. This one used to live in the s's, but it got promoted to the 3ds. In other words, it is the adult in the front of the minivan that got sent back to sit with the kids to make them stop moving. Now, these 3D electrons right here are not going to move. They are not going to double up because that would cost energy. The only reason they could move around before is because there was no energy cost to it. So this configuration right here is the correct configuration for chromium. All right, so we're going to talk a little bit more about the irregular configurations and about chromium. But any questions on anything so far here with the idea that chromium is irregular because it has promoted an electron from the s to the d's to stabilize those d electrons so they don't bounce around anymore? So Andrew, let's see. Yes, I see what you're saying. There was a, yes, I see what you're saying. There's a dollar sign in there, and I was a little confused if that was some kind of text talk that I was not cool enough to understand, but I think you just hit the shift key while you were doing the 4 there. So yes, that is correct. So what's going to happen if we take this right here? This was our regular configuration, and now we're going to make it irregular. All right, so instead of a 4s2, we now have a 4s1, and instead of a 3d4, we now have a 3d5. So we have promoted one. Thanks for clearing that up, Andrew. So yeah, we have promoted one electron from the s into the d's. So these are the proper configurations for chromium. Chromium is an irregular element, and so these are the proper configurations. So any questions on what we've done so far with chromium? All right, so let's go back. And what I'm going to do is I'm going to go ahead and X these out just because it is not the proper configuration. This is not the proper orbital diagram. These are the correct ones. So again, I X'd out the ones we did at the beginning because those ones were not correct. Chromium is irregular, and it's something I'll ask you to remember, that chromium is irregular, and chromium promotes one s electron into the Ds, and that's how we get the proper configuration for chromium, because it is irregular. All right. Questions on anything here? All right. So before we go on, let's talk about our irregular elements. So there are 4 elements that I want you to memorize as being irregular, and they all do the exact same thing. They take one s electron and promote it up into the Ds. So the 4 elements I want you to know: chromium, copper, molybdenum, and silver. And I'm going to talk about those for just a moment, but any questions here? So the D's and the F's have lots and lots of irregulars. So if you're ever doing configurations just to practice, and then you look at a table and you're like, hey, I didn't know that one was irregular. The teacher told me there was only 4 irregulars. Well, there are actually lots of them. I'm only making you memorize 4. And anything else I give you on a test or quiz will be a regular configuration. But just be aware that there are lots of irregulars throughout the D and the F block. So what you are responsible for will be regular elements in the S and P, D and F, plus these 4. So any regular element I could give you, and these 4 irregulars I could give you. Questions on anything here? Anybody need this slide for a little longer? Okay. So let's talk a little bit more about these irregulars. All right, so here are the irregulars I want you to know. And again, remember there's lots of irregulars throughout the D and the F block. It's just that I'm only making you learn 4 of them. Every one of these will have an S1. The 2 that I'm looking at right now, chromium and molybdenum, will have an S1 and a D5. And these 2 right here will have an S1 and a D10. So something that we'll talk about probably next class is that there is what we call a special stability associated with a full or half full shell. That means if you can reach a D10 or a D5, you will be much more stable. And there is a special instability with being 1 electron short. So for these, they have a really good reason to promote that electron. So one reason is they stop the bouncing around, but the other reason is that they are extremely stable. Again, once they have a fully filled shell, they have all 10, or they have a half-filled shell. They have perfect half of what they need. All right, so I'm going to talk a little bit about copper, but any questions so far about the 4 irregulars that you need to know? Okay, so let's talk about copper next. So here is our copper, and I'm going to start it off the same way. And I'm going to say if copper was a regular element, and we all know it's not a regular element, but I want to just pretend. Every once in a while, copper looks in the mirror and is like, hey, can't I be normal like all the other elements? So we're going to pretend it's normal just for a moment. All right, so here's the copper that we're looking at. And the first thing I'm going to do is take a look at its noble gas core. So I'm going up and all the way to the end. And there it is, it's argon. And then I would come right over here and say we're in the fourth energy level, the S block. And there's two elements here. So that's 2 right here. Then we're moving into the D block. And so whenever we go into the D's, we go down to the 3s. So from 4 down to 3. Then we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. So this is 3D9. This would be the regular configuration for our copper. So any questions on this right here? It is the regular configuration. Although we know copper to be irregular, so we're going to modify it in just a moment. All right, so if it was regular, it would look like so, but it is not. Copper is irregular. So we mean that in a loving way. We're not trying to insult copper. All right, so what do I have to change about this electron configuration? What should it really look like? So it's not really 4s2, 3d9. What is it? Excellent. Seeing a lot of 4s1s, 3d10s coming across. And Clinton is correct. You do need that argon out in front. So argon 4s1, 3d10. So I'm going to take that highlighter and I'm going to cross this one out and I'm going to put a check mark here. So it is not a regular element. We would expect it to be the argon 4s2, 3d9, but it is really argon 4s1, 3d10. Any questions about this, about how we turned it from a regular element into irregular? Okay, before we go on, I want to do its orbital diagram. Oops, did I hear a question coming through? No? Okay. I was just imagining things. All right. So here, I'm starting off with that argon again. 1 line for S's, so 4s has only 1 line. Always 5 lines. Oops. 5 lines for our D's. This time we have only 1 arrow, 1 electron in our 4s's. Now I'm going to put 10 in the D's. So obviously when you're drawing it out, it's always your choice on how to draw, but my recommendation, so you remember the rule, is give everybody 1 electron before you give anybody 2. So 1, 2, 3, 4, and 5, and then come back. 6, 7, 8, 9, and 10. That way you just remember that rule, always giving everybody 1 before anybody gets 2. All right, so this is an extremely stable configuration because everything is paired up here in the D's. Nobody can bounce around. All right, so any questions on how we did the irregular configuration for copper, the electron configuration, or the orbital diagram for copper? So I am going to warn you that when I give you your next exam, there is a fair chance you're going to see an irregular on there. There are only 4 irregular elements. Let's go ahead and call these irregulars. There's only 4 that I want you to know. So please make sure that if I give you one of these elements, you know they're irregular. So every once in a while, when I give this on a test, at the end when they get it back, they're like, hey, you didn't tell me I was looking at an irregular. How was I supposed to know chromium was irregular? So I'm telling you now, memorize these 4 elements as your irregulars. Chromium, molybdenum, copper, and silver. Every one of them will take 1 electron from its S and put it into the D's. So you will have an S1 for all of them, Chromium and molybdenum will have a D5, and copper and silver will have a D10. Let me go ahead and label this a little better. There we go. All right. Any questions on what we've been talking about for the regular or irregular configuration, or that there are these 4 elements that I need you to memorize as irregulars? And if I do ask for their electron configuration or orbital diagram, you do not have to give me the regular one. All I need is the irregular, but if it helps, you can always do the regular, cross it out, and then do the irregular. So questions on anything so far? So I know this is sort of jumping you straight into the electron configuration, and for some of you it's been a while and you didn't get a chance to watch those videos yet. But any questions at all so far about the electron configurations or orbital diagrams? You're all really quiet, but I know this is a tricky topic for a lot of people. So if you would like more help on it, please feel free after lab to stay and we can practice electron configuration. All right, so let's move on to electron configuration of ions. Let's grab ourselves a periodic table. All right, so we're going to start off looking at sodium. So if we were looking at sodium, I want to know what the full electron configuration is, no abbreviations for a regular old sodium. So I want you to try that on your paper, and then if you're brave enough, go ahead and type it into the chat box. So electron configuration for regular sodium, no abbreviations, just a full configuration. So I'm seeing a 1s2, 2s2, 2p6, and 3s1 from Angie and Chris. Excellent. And Jervin's getting the same thing. Excellent. So let's take a minute or two longer, let everybody have a chance to find those configurations. Looks like Andrew's getting something similar. Excellent. And Paso got the same one. Great. All right, go ahead and click in if you'd like more time to work out that electron configuration, or if you're ready to go over it. All right, so it looks like pretty much everybody is ready to go over it, except some, I was going to say some person who's too scared to vote, but I got everybody now. Excellent. All right. So I'm hearing 1s2, 2s2, 2p6, and 3s1. So let's go over how we got that. So first row, S block, and we have 2 elements, and that's the 1s2. Then second row, S block, and we had 2 elements. That is our 2s2. And then second row, P block, and we had 6 elements. That is our 2p6. And then third row, we're in this S block, first element, and that is the 3s1. So any questions about how we got this configuration, 1s2, 2s2, 2p6, and 3s1? All right. All right, so that is the regular configuration for sodium, but now we want to look at sodium plus. So if we have a positive sodium, has that sodium gained an electron or lost an electron? Excellent. So I'm seeing a lot of lost in there. So this sodium has lost one electron. Let me actually write out that word electron. One of those electrons got lost. Which one? Which electron are we getting rid of? All right, so I'm seeing lots of 3s1s, and you are correct. So for sodium plus, we have lost one electron. That means we have to reach in and grab an electron out of this electron configuration, and we will be taking off the 3s1. So the rule that we're going to use is we always take away the one from the highest energy level. So if we look at our energy levels, we have 1, 2, 2, and 3. 3 is the highest energy level. It is numerically the largest, and it also is the furthest from the nucleus. So if you remember way back when, last class, we talked about the first energy level, second energy level, third energy level, and so on. I realized my third energy level wasn't a very good circle. Still a bad circle, but you get my point. All right, so as we go further and further from the nucleus, it is actually easier to remove an electron. Those of you going on to organic chemistry, you're going to learn about something we call an electrophile. So an electrophile is something that loves electrons, but it's also a thief. So it swims around in solution and it looks for an easy electron. It looks for the person who left their bike out and didn't lock it up. So it's swimming around and then it grabs an electron and runs off with it. So what it's trying to do is get an easy electron. A 1s electron is not very easy to take. It is very close to the nucleus. However, a 3s electron is much easier because it is not very close to the nucleus. So the nucleus is the positive charge. It is what draws the electrons in. It draws the electrons towards itself. However, if you are further from that positive charge, you are less likely to be connected to that nucleus. So again, the highest energy level, which for us is 3, is going to be the furthest one out from the nucleus, and it will be the easiest for something to steal. And that is exactly what happened. That's how it became Na+. So something came along and stole that electron. So what I'm going to do is rewrite this configuration. So the true configuration, 1s2, 2s2, 2p6. This is the correct configuration for Na+. So any questions on the fact that we did remove an electron, we didn't add one, or which electron we stole from this sodium? Okay, so next up we're doing chlorine and Cl-. So chlorine and chloride. So I want you to find the configuration for chlorine and also for Cl-. So find those two electron configurations. And chlorine is right over here. If you'd like, you can use the noble gas abbreviation on this one. So I'll leave that one up to you if you want to use that abbreviation. All right, so I see a configuration from Clinton and I'm sorry, Clinton, is that Cl or Cl minus? All right, Cl, excellent. And it looks like Andrew got a similar one, and Jervin has a similar one as well. And Jervin is suggesting that it will be a 2p6 for Cl minus. What do you all think of Jervin's suggestion that chloride Cl minus will be 2p6? Sorry, I said Jervin says 3p6. Okay, and then Angie agrees. So let's take another minute or so for those of you still working on it. And it looks like Maria got the same as Jervin did. All right, so I'm going to go ahead and put up that poll again. Go ahead and click if you'd like more time or if you're ready to go over it. All right, so it looks like we got a couple people who would like a little more time. So let's take another minute or so, and then we'll go over it. All right, so let's go ahead and go over these. So starting with the Cl, so here, first energy level, this is the S block, and we have two elements that belong to it. So that was the 1s2. Move this away. There we go. All right, next second energy level, S block, two elements, so 2s2. Then second energy level, P block, 6 elements, 2p6. And then third energy level, S block, 2 elements, 3s2. And then third energy level, P block. And we go across 1, 2, 3, 4, 5, and we get 3p5. For those of you who chose the noble gas configuration, you went up and to the right, and there it was, neon. So you started off with your neon, and then from there, 3s2, 3p5 like so. So any questions on how to do regular chlorine? So let's go ahead and copy this one up. All right, so next up we had Cl minus. And I saw correctly when you guys were working on it, for a negative, we need to add an electron. And when we're adding an electron, the same rule applies. We're adding it to the highest energy level. And if you have two different 3s, a 3s and a 3p, the p is higher and it's going to take that extra electron. Also, the s was full, so there was no way to put it into the s. So this is a 3p6 and a 3p6 like so. All right, so any questions on anything here? Any questions on anything with electron configuration so far? All right, let's go ahead and take our break. So let's come back at 6:05. And I'm going to step outside just to get some air for a moment because it's really, really hot in here. And I will be back in just a little bit and we'll get started at 6:05. All right, so let's go ahead and get started again. So before break, we were talking about the electron configuration of ions. And so we're going to continue with that. But now we're going to be talking about our D block ions. So D block ions follow the same principles, but they look a little different. So I'm going to start off looking at just regular iron, and then we're going to turn that into iron 2+ and iron 3+. All right, so first let's find our iron. It is right here. There we go. All right, so starting off, I'm going to use the noble gas configuration, the noble gas abbreviation. So I'm going to go up and all the way to the right, and we are looking at argon to start with. And this is for iron. So then we're going to have 4s2. And then anytime we go down to the D's, then we go down in number. So here we're at 3D. And 1, 2, 3, 4, 5, 6. So iron is argon 4s2 3d6. So any questions on how I got that configuration for iron? All right, so let's copy that up. All right, now I want to use that to make iron 2+. So if it is a +2, that means it's lost 2 electrons. And that E- is my symbol for electron. So we need to take 2 electrons away. And our rule was we take them from the highest energy level, and that is the largest number that we've got. So do we remove them from the 4s or the 3d? All right, so I'm hearing some votes for the 3d. Remember, if we're looking at our atom, in the center is the first energy level, and then we get to the second, third, and finally the fourth. We need to take them away from the electron that is furthest out from the nucleus. We have to take them away from the orbitals that are furthest away from the nucleus. So let me go ahead and ask one more time. What do we think, 4s or 3d? Where are we going to take our electrons away from? All right, excellent. So it sounds like we've got more agreement on that 4s. There we go. And it is indeed the 4s that we need to remove them from. So if you can remember that we're always after the highest number, that will help you remember, because the highest number is the furthest from the nucleus. The other way to remember these is in the D block, we're going to be removing the s electrons first. The reason we're removing them is they're further out because they're at a higher energy level. So the true reason is really that 4 is greater than 3, meaning they're further from the nucleus. But a lot of students just remember, hey, in the D block, take the s electrons first. And that's exactly what happens. So there's 2 ways of writing this. So the easiest way, I think, is saying AR 3d6, but some students don't feel comfortable leaving out the 4s. So another way that you could write this is AR 4s0 3d6. And that little notch right there should have been a 0, like so. All right, so any questions about what we did here, about how we found our electron configuration for iron 2+? All right, so next up, we have our iron 3 plus, and what we know is that a 3 plus means it's lost 3 electrons. All right, so if I take the original configuration, let me grab this one right here. All right, we need to take away 3 electrons. We know the first 2 are coming from the S, so those 2 are gone. There's only one last place for us to take electrons from, and those are the 3 Ds. So our third electron comes out of the Ds, but the first 2 come from the S's. So our electron configuration now is argon 3d5, or if you prefer, 4s0 3d5. All right, any questions on how we did our iron 2 or our iron 3? All right, so let's do our silver next. So we're going to do Ag, and we're also going to do Ag+. So here's our silver, and I want to remind you that silver is an irregular element. So let's start off with the noble gas core, and that's going to be chromium. So we're starting off with chromium. What comes next? Remember, this is an irregular element for standard old silver. What should come next? All right, so I'm seeing a 5s1 from Andrew. And then what comes after the 5s1? 4d10, excellent. Good tag team work there. Excellent. All right, any questions on how we tackled this irregular element, silver? This is the standard configuration for silver when it is not an ion. Chromium 5s1 4d10. All right. All right, next up, we need silver plus. So anyone want to bravely type in what they think the configuration for Ag plus is? It does start with chromium, and then what comes next? All right, so I'm seeing a few different answers, so let's go ahead and talk about this. So here it's got a positive charge. So a positive charge means it has lost an electron. And I see a few of you adding electrons in. Be careful, it has lost an electron. And where it has to lose it from is the highest energy level. So it has to leave from the 5. But again, another way to remember this is our D block will always lose its S electrons first. So I'm going to cut out those S electrons, and it will be a 4d10. So let me take it away. Any questions on why Ag plus is krypton 4d10? I saw a few other things in the chat box, some other ideas, but any questions why we would do it this way? Now is a great time to ask questions because, the day of the exam gets stressful, so. Okay. Yeah, I'll just leave it below because I think this page is getting too busy with too much stuff. All right, so next up, I want you to try zinc and zinc 2 plus. So I want you to do both zinc and zinc 2 plus. Zinc is right over here. It is not irregular. It's a standard old element. So find the electron configuration for zinc and zinc 2 plus. All right, and it looks like Clinton made a suggestion for zinc. What do y'all think of Clinton's suggestion? All right, lots of agreement on that one. Excellent. So keep on working on getting the zinc 2 plus then. And thank you, Clinton, for being brave and being the first one to type in. So y'all are doing zinc and zinc 2 plus. Right. All right, and so Andrew is suggesting argon 3D10 for zinc 2 plus. What do y'all think of Andrew's suggestion? All right, so we got some agreement on that. Excellent. And thank you, Andrew, as well, for being brave to be the first one to type in for that one. All right, go ahead and click in if you'd like some more time before we go over it, or if you're ready to go over it. All right, so it looks like just about everybody, or at least everybody who's voted, is ready to go over it. Never know what to think about the few people who don't vote, if they need more time or they've stepped away from their computer. All right. So for zinc, you went up into the end, so you started with argon. And then you had 4s2 and 3d10. So any questions about how we get the electron configuration for regular zinc? All right, so that was our zinc. And what we said for our transition metals and really any element is that we always take from the highest energy level first, and that translates into taking the s electrons first for transition metals, for d block elements. So it is the s's that go away first, and it becomes AR 3d10, and you're welcome to say for S0 in there as well if you prefer. All right, so any questions on anything here? All right. Actually, put these out of the way. All right. So next up, I want to talk about the idea of paramagnetism and diamagnetism. And we're going to come back to these topics later on in the course. But just to get you started with them, something that's paramagnetic has unpaired electrons. And that's kind of weird because it starts with the term pair. And so you want to say para means paired, but it does not. So para means it would like to be paired, but it is not. It is unpaired. So it's kind of a word trick there that you just kind of got to find a way to remember that paramagnetic means unpaired. And we've done so many little arrows, I figured it was time for a change. So the little boy waving at you, that is the arrow here. All right, so these are unpaired electrons. They do not have a second electron in their orbital, so they are paramagnetic. So next up we have diamagnetic. So diamagnetic means all of the electrons are paired up. That means you have an arrow up and an arrow down. So every electron has a partner in its orbital. So any questions on anything here so far? Okay, so these are vocabulary words that I definitely want you to know. And again, we're going to return to this in I believe it is chapter 10. So what we're going to be seeing is a paramagnetic substance. We have the atoms and ions attracted to magnetic fields, and in diamagnetics, they are not attracted, and in fact, they'll have a slight repulsion. But this changes the magnetism, whether or not they are paired up or unpaired. So the paramagnetic, where they are not paired up, they don't have anything to cancel out their spin, the electrons spinning around, so they are very attracted to those magnetic fields, whereas the diamagnetic, this is arrow up and arrow down, or if you think of the electrons themselves, they are spinning in opposite directions. They are canceling out each other's magnetism. So we don't see an attraction, or we see actually a slight repulsion to the magnetic fields. So again, these are vocab words that I want you to know. Paramagnetic and diamagnetic. So any questions on anything here? Okay, before we go on, just for some fun, here's a configuration that we did today. So if I am looking at this one right here, is it paramagnetic or diamagnetic? All right, so I'm hearing lots of paramagnetics. Excellent. So this is indeed, let's squeeze it in right here. Paramagnetic. Any questions on why we would call this paramagnetic? You only need one unpaired electron to call it paramagnetic. Here, everything's unpaired, but again, you would only need one unpaired to call it paramagnetic. All right, so here we were looking at copper. Paramagnetic or diamagnetic? So remember, you only need one unpaired electron to call it paramagnetic. Take a look at all the electrons. Excellent. So I think I changed your mind a little bit there. So that is indeed paramagnetic. Remember, it only takes one electron that's unpaired to create that attraction towards a magnet. So any questions on this one about why it's paramagnetic, not diamagnetic? All right. Look at how much fun we've had today. Okay, I've had fun. You guys might feel like you're being tortured. All right. Okay. So next up, I want to talk about the idea of an isoelectric configuration. Tasso, you're so nice. You always laugh at my bad jokes. All right. So here we have sodium and we have neon. And let's open up a new page so we have some room. All right, so I'm going to start off with sodium. So if I want the electron configuration of Na+, I'm going to start off with 1s2, 2s2, 2p6, and then do I need to put anything else on here for sodium plus, Na+? So any questions on how I did sodium plus? I left off the 3s1 because sodium has lost that electron. Okay. So let me copy this one up. That is our sodium plus. Next up, let's look at neon. What's the electron configuration for neon? What do you guys think? What would the electron configuration for neon be? Excellent. Excellent. I'm seeing that it is the same, and it is indeed 1s2, 2s2, 2p6. Any questions on how sodium plus and neon would be the same electron configuration? All right, so let's bring this one up. So this is indeed two different elements, one an ion, one a neutral element, and they have the same configuration. I should say same electron configuration to be specific. And this is something we call isoelectric. So if two things are isoelectric, it means they share the same electron configuration. And once upon a time, I told you that the noble gases were the rock stars in the periodic table, and everybody wants to be like the rock star. And the whole reason that the other elements are forming ions, and the reason that they are predictable in what charge they take, is because they're always trying to be isoelectric with the next noble gas, with the nearest noble gas, I should say. So the reason sodium becomes a 1 plus is so it can take on neon's electron configuration. The reason magnesium will take on a 2 plus is so that it can match neon. The reason aluminum takes on a 3 plus, again, is so that it can match neon. The reason fluoride becomes 1 minus is to be like neon. The reason that oxygen takes on a 2 minus is to be like neon. The reason nitrogen takes on a 3 minus, again, it's all to be isoelectric with neon, to have its electron configuration. So you guys thought I was kidding around, but neon is a serious rock star. Everybody is trying to copy neon. So these are isoelectric ions with neon. They take the same electron configuration as neon does. So two elements or ions with the same configuration are said to be isoelectric. Same electronic configuration. So any questions on this idea of isoelectric so far? Okay, and this is a vocab word that I want you to know, isoelectric. All right, so what you're seeing on the screen right now is what we call an isoelectric series. All of these elements and ions are isoelectric with each other. So if you look at their electron configuration, their electron configuration is identical. That's what makes them isoelectric. So when we have more than two that are isoelectric, we do refer to them as a series. Don't worry about that word series. You don't have to memorize that. But one thing that I do want you to know is their relative sizes. So what we find is the one that is most negative will be the largest. The one that is most positive will be the smallest. And there's a reason for that. When we look at their protons, remember the protons are in the center, the protons are positive, and they are pulling in, they're raining in those electrons. The more protons they have, the more they are going to magnetically pull their electrons towards themselves. So here, scandium has 21 protons in its core, and sulfur has 16. So what always happens in these isoelectric series is the one with the greatest positive charge will have the greatest number of protons, and it will be the smallest. While the one with the greatest negative charge is going to have the least number of protons, the least positive charge pulling the electrons in, and it is going to be the largest. So let me write that out. So in an isoelectric series, and I'll list this one as an example. So in an isoelectric series, the sizes are going to be largest for the most negative and smallest for the most positive. And they will go in that order. So the sulfur is going to be the largest, followed by chloride, potassium, calcium, and then scandium being the smallest. So the reason, again, is based on the number of protons in the center, that the most positive one will have the greatest number of protons. It's the furthest down on the periodic table, so it's better at reining in those electrons. But what I'd like you to know is in an isoelectric series, the sizest is going to be the largest for the most negative and the smallest for the most positive. So the radii or the size So any questions about that, about what an isoelectric series is, or what the trend is in the size, that the greater the negative charge, the larger it is, the greater the positive charge, the smaller it's going to be? Let me give you a moment to copy. And Andrew's asking if it always correlates to the number of protons. And yes, it will always correlate to the number of protons because protons are the reason it happens. So yes, it does always correlate with protons. Good question. All right. Anybody need some more time on this slide to copy down? All right. So next up, we're going to talk about valence electrons, which are our outer electrons, And I think we talked about this way back when, maybe in chapter 1. And those of you who had the intro class, you probably talked about this as well. So our valence or outer electrons are the electrons in the outermost energy level. So if you're looking at that atom again, and here's the first energy level, second, third, fourth, and so on. These are the electrons the furthest out from the nucleus. They control reactivity and bonding. So if any electron is going to be lost, it's going to be lost from the valence electrons. If it's going to gain an electron, it's going to be put into the valence electron shell. So it's always the outer electrons that we care about. And here it says the highest N, where N is the energy level. So N would be 1, 2, 3, 4, and so on. N is that energy level. So any questions on anything here? All right, so there's a couple ways to count valence electrons. One way that has no exceptions is counting from left to right, but skipping over the D and the F block. The reason we skip those is because our standard valence electron rule doesn't count for them. They do a special valence electron rule. So we are only counting the S and the P, the electrons in the S and the P elements. So if you count from left to right, it will never fail you. However, there is another way that's actually much more popular. And the other way, and most of you know this, is just by looking up at the top of each of the columns. So you're looking for the number next to the A. So here it says 1A. That means 1 valence electron. Next up we have 2A. We're going to skip all of the D's. We're also skipping all of the F's. Then we have 3A, 4A, 5A, 6A, and 7A. That tells us how many valence electrons are in each of those columns. And here we have 8A. But the problem with this method is that pesky little helium. Helium's a noble gas, but remember it has another home. That other home was right over here. Helium has 2 valence electrons. So the rule of looking to the top of the column to get your valence electrons works perfectly except for helium. You've got to remember helium is an S block element and it has 2 valence electrons. Like so. All right. So these again are the outer electrons that we use in order to do all of the chemistry. So any questions on counting valence electrons? All right, so we are up to quantum numbers. So I talked about quantum numbers briefly way back when, and I said they're kind of like a coordinate system. So if you think about your math class and they say, hey, this dot should be at x equals 3, y equals 4. These are 4 numbers that will tell us where our electron is. So these 4 numbers are characterized by this right up here. And this is n, which is going to be our principal quantum number. That is your energy level. It has L, and L is called the angular momentum number, and L is the orbital type. And that means it is S, P, D, S, P, D, or F. Here we just give a number to each of those orbitals. So we'll give a number to the S, a number to the P, D, and F, just so we can express it numerically. And L will have numbers from what we call L equals 0 to n minus 1. Don't worry about that rule. I will show you an easier way to do it. Then we have what we call the magnetic quantum number, m sub L, and that is telling you which one of the P's, of the D's, and of the F's you're looking at. Which P, D, or F are we looking at? And finally, at the bottom, we have the spin quantum number. And so for the spin quantum number, this is saying, do you have arrow up or the arrow down? In other words, is this spin up or spin down? So if you had an s orbital, you have one going up, one going down. And again, we've given these numerical values. And if you're wondering, well, why the numbers we gave them? Why call a spin a 1/2, positive and negative? They use these in physics as they're calculating larger things. We also use them in chemistry, computational chemistry, and when we're trying to add up the total spin for a molecule. So these numbers do actually have a reason, but for what we're doing here, I'm going to show you how to use those numbers to get the quantum number, but we're not going to go into the calculation of adding up, say, all the spins of all the atoms in a molecule, because that's more upper division stuff. So we're just laying the foundation for when you become chemistry majors, and then you get to do all that fun stuff. All right, questions on anything so far? We're going to go into more detail on each one of these, but any questions so far? All right, so we said that first we have N, and N was your energy level. And then we said we have L, and L was your orbital type. So I want to go over the values for L. So it is possible for you to use what's given here, 0 to n minus 1, but I feel like that is more complicated. Those of you who know it, you're familiar with it, you're happy with it, please go ahead and use it. But what I do is I start with 0, and I say 0 is my S. And then I go in order. So the next orbital we talk about is P. P has a 1. Then we have D, which is 2, and F, which is 3. So the most common mistake on this is people want to call S1 rather than 0. Because normally when we're counting, we don't start our count with 0. We start it with 1. So my recommendation, let's say you are doing your homework, you're doing a test, you're doing a quiz on your scratch paper, write this out for yourself somewhere. Start with 0 and say 0 is S, and then just 1 is P, 2 is D, 3 is F. That way you don't have to worry about it, and you won't in your head make that mistake of calling S number 1. So remember, these are just assigned numbers for each of these orbitals, so that when we get our set of numbers, we will know which orbital we have by which one of these numbers we have. So any questions on anything here so far? All right, so next up, let's talk about ML, or we call it M sub L. And I said it corresponds to which one of the orbitals. So I'm going to start with P because I think it's a little clearer to see it with P. So we said we have 3 types of P. So P, we had a PX. This is an orbital that looks like so, that lies on the x-axis. Then we had a PY, same shape, but it lies on the on the y-axis. And then we have PZ, again, same shape, but it lies on the z-axis. What we're trying to do is turn everything into numbers here. We don't want to deal with P's and X's and Y's and Z's. So instead, we're going to call this -1, 0, and +1. So the way it works is the L over here said P was 1. So in the ML, We go from -1 to +1, always pausing at 0 in the middle. And this way we can numerically say which one of those p's it was. Was it px, was it py, or was it pz? So I think ML is the toughest one to wrap your heads around. So is there any questions about how we're going to label each of the p's? We have px, py, and pz, but we're going to call them -1, 0, and +1. So if I happen to have an electron here, I could identify it by calling it that +1. But if instead that electron was over here, I could identify where it was by saying that it was in the -1 p orbital. Any questions so far about that ML? All right, so let's move on to our D. And we talked about the Ds earlier today. How many different types of D orbitals do we have? Anybody remember? Excellent. So I'm seeing 5. So I told you when you're doing the orbital diagrams, you'll always write out 5 lines, 1, 2, 3, 4, 5 for the Ds. And I also told you you're not responsible for knowing the subscripts up here that you would for the D orbitals. I want you to know the ones for P's because they're pretty simple, Px, Py, Pz, but I'm not going to make you memorize all the D ones. Here for the Ds, remember D was labeled 2, D was labeled 2 here. So what we're going to do is go from -2 to +2. -2, -1, 0, +1, and +2. So again, this is a numeric way of assigning a value to each one of these d orbitals. So if I had the electron here, I have a way of telling the world where my electron is. Likewise, if this electron was over here, I would have a way of telling the world where that electron is. So any questions so far on the P or the D? All right, so lastly we have our F. And once upon a time, I told you that we have 7 F orbitals. So if I'm going to draw lines, I'll draw 7 lines. 1, 2, 3, 4, 5, 6, 7. And if I look over here, F is labeled as 3. So what do you think the value right here is going to be? -3, excellent. So F's will go from -3 to +3, -3, -2, -1, 0, +1, +2, and +3. So again, this just is a way for us to tell the world, hey, this is the F orbital that my electron is in. So any questions on the P, the D, or the F? All right, so I skipped over the S, and I want to come back to that. So the S has only one type of orbital, just that solitary one. And S up here is 0, and so that's exactly what we're going to label that S orbital. We're just going to call it 0. And let me move these around so we have everything in line here. All right, so what we see is S is 0, P is from -1 to +1, D from -2 to +2, and F from -3 to +3. Any questions on these values? And these are your ML values, or we call it M sub L. All right, so lastly, we have our M sub S, and this is our spin. So for the spin, you could be arrow up or you could be arrow down. So we refer to this as +1/2 or -1/2. So that way we can tell the world, hey, my electron is spinning clockwise or counterclockwise. Okay, so I know this is a lot of stuff, and we're going to go over all of it. Let me try to get it all on your screen. There we go. All right, so questions about anything that we've talked about here? All right, so let's go ahead and talk a little bit more about these, and then we will put these into action and use these. So first off, here's a chart just for reference. It talks about everything that we just said. Here's your energy levels. Here is the L. So in the first energy level, there's only the S. In the second energy level, there's a 0 and a 1, meaning there's an S and a P. And for the P, there's the M sub L. So this one goes through everything in detail. You don't need this, but some people find it helpful when they're working out problems. So I'm leaving it here just as kind of optional. So let me put a note here that this is optional. Please don't feel like you need to memorize this or anything else. So this is optional. If you find it to be helpful, feel free to use it. If not, don't worry about it. All right, so when we do our quantum numbers, we have to use the Pauli exclusion principle. So that says no two electrons in the same atom can have the same set of quantum numbers. In other words, one orbital can only hold 2 electrons, and they must have different spins. So in other words, you can never get in one orbital 2 electrons spinning the same direction. If they are stuck in the same orbital, one arrow up, one arrow down. So another way to think of these quantum numbers is think of them like a student ID. No 2 students can have the same student ID. I have had classes where I had 2 people with identical names. First, middle, and last names were identical. So their student ID was really helpful when I put in grades to make sure I was putting in the right grade for the right person. So if you would like to, you can think of these quantum numbers as a student ID. No 2 electrons can have the same student ID. All right, so questions on anything here? All right, so next up, we're going to write out some quantum numbers for each of these, but I think it's about break time, so let's go ahead. I know it's 6:52, but let's go ahead and come back at 7:05. The reason is just here it's really hot and the computer's kicking off even more heat. So let's come back at 7:05. So we will finish up our quantum numbers, and then we will talk about the lab. So you'll probably get out of here by about around 8:15-ish tonight, unless you'd like to stay. And of course, I'll be with you till 9:45 tonight. Oh, and I see, scroll up to the last slide. This one right here. Yes, okay. So let's come back at 7:05. And I'm going to go ahead and pause that video. Okay, so let's go ahead and get started again. So any questions from what we did before break? All right, so next up, we are going to look at the quantum numbers for each of these elements given. And we're going to start off right at the top with the electron and hydrogen. All right, so the first thing we're going to need is the electron configuration for hydrogen. So I'm going to go over to our periodic table. And here's our hydrogen. In first row, it's in the S block. And there's 1 electron, so we're going to call it 1s1. Any questions on how, it looks like a fraction when I put it that way, on why hydrogen has a configuration of 1s1? All right, so let's go ahead and label hydrogen 1s1. All right, so now what we want to do is take this and turn it into the quantum numbers, N, L, M sub L, and M sub S. All right, so first our orbital diagram, 1s, and I'm going to go ahead and put my arrow up. There's no reason it has to be up. I could put it down, but I'm going to go ahead and just say 1s1 with the arrow going up. So N is my energy level, and that will be 1. So N is 1, and it comes from right over here. So next up, we're going to do S. And one thing that I recommended that you do is you write out S, P, D, and F, and then you write their L values. So S was 0, P is 1, D is 2, and F is 3. So for L, because we are in the s orbital, it has an L value of 0. Any questions on how let's see, Driven, I'm not sure I understand your question. Not 0. Oh, okay, sorry about that. Okay, all right, so we said that S takes on the value of 0. So for L, we're going to put in 0 for S. Any questions on how we did N or L so far? All right, so next up is our M sub L. And we said for P, it was -1, 0, and +1. For D, it would be -2, -1, 0, +1, and +2. And then for F, -3. Give myself a little more room here. All right. Sorry, formatting issues there. All right, so -3, -2, -1, 0, +1, and +2. But we said S was just a 0. So this 0 will be the ML value, like so. There's only one type of S value, so if you ever put S for your L, you must put a 0. I'm sorry, if you ever put a 0 for your L, you must always put a 0 for your ML. So sometimes students say, does that mean if the second number is 0, the third number is also 0? And the answer is yes. If you put a 0 for your first value, I'm sorry, let me say that one more time. If you put a 0 for your second value here, your third value must also be 0. So in other words, whenever you have a 0 for your L, your ML is also 0. All right, any questions about that ML value? All right, so next up is the spin. So your spin, screen is stuck, that's okay. All right, so our spin value, I will put it over here for the moment. M sub S is going to be either +1/2 or -1/2. Let's see, I already used green. Use silver. All right, so I'm going to use my MS. It's going to be the arrow up, so I'm going to go ahead and say the MS is +1/2, like so. Oh, you're right. Thank you. I forgot to put in the +3. Thank you, Tasso. All right. Other questions about anything here? Okay, and my screen is still stuck, so give me just a second. There we go. All right, now let me put everything together. All right, so here's our little reference table. All right, so any questions on how we did the quantum numbers for hydrogen here? All right, so next up, we have helium. So helium has an electron configuration of 1s2. Any questions on why helium is a 1s2, or anybody want me to show on the periodic table how I got that 1s2? All right, so next up, let's do our orbital diagram for helium. 1s, and we've got 2 electrons. One will be arrow up, and one will be arrow down. Because there's 2 electrons, we are asked to do the quantum numbers for both of those electrons. That means we're going to have 2 sets right here of quantum numbers. So I'll start with the first one, this one right up here. So it has an energy level of 1. Make sure I get my colors correct. So this one comes from the one right here. Next up, we need S, and we said that S would be 0. So right over here represents the S, and we said that would be 0. Next up, we have the M sub L, and we said for S's, this would always be 0. So that is 0. And now if I decide that I'm going to do this electron right here, I'm going to call this plus 1/2. Any questions on how I did the first electron here? How I did the quantum numbers for that first electron, the one that I colored in purple? All right, so now what I want you to do is I want you to do the second one. Do this one that I just colored in black. So find the 4 numbers that correspond to it. When you've got those 4 numbers, go ahead and type it into the chat box. All right, so I'm seeing 1, 0, 0, minus 1/2 from Tasso. What do y'all think of Tasso's answer? All right, it looks like Andy got something similar. And Maria, excellent. It looks like Juan and Kimberly as well, and Jervin, excellent. And it looks like Sarah got something similar as well. All right, I'm going to go ahead and launch the poll. So go ahead and click in if you'd like some more time or if you are ready to go over this one. So it looks like just about everybody is ready to go over it. All right, so those numbers are looking good. First energy level, S orbital. There's only one type of that S orbital. And we're going to call this negative 1/2 for the spin because we have the arrow going down. Are there any questions on how we're doing our quantum numbers here for helium or for the one in hydrogen? How are the quantum numbers feeling so far? Does it feel like doable? Maybe? Yes? Excellent. So I'm going to take Jessica's yes as a yes for everybody. Okay, so Tasso said they're going okay. I can take an okay. All right, so let's keep practicing. Oh, my screen's stuck again. Give me one sec. There we go. All right, so we got a few more to practice. Next up, we're going to do the 3 electrons in lithium. So if I were to do the electron configuration for lithium, I would say 1s2, 2s1. Any questions on how I got that, or anyone want me to show them on the periodic table how I got that configuration? All right, so next up, let's do its orbital diagram. 1s, 2s. Now in the 1s, there's 2 electrons, so we know that means one has to be arrow up, the other one arrow down. For the 2s, it doesn't really matter. Let's see. Good question. So Clinton's asking whether it matters which way we put the arrows, and no, the answer is it does not matter which way you put the arrow. So let's say I wanted to go, spin down and then spin up, and let's say I wanted to make this one spin down. That's fine. We just have to do the corresponding quantum number. So we could also think of carbon. So this is kind of an aside. So this is carbon. 1s2, 2s2, and then I believe 2p2 for our carbon. Yep. So we're forced into doing a spin up and spin down for the s's. However, for the p's, I could put one here and one here, or I could put one here and one here. So I could do it however I want, up or down. In this 2p's right here, I just want to do the correct corresponding quantum numbers for whatever I've drawn here. All right, good questions. Any other questions? All right, so let's go ahead and do this. And by the way, the reason that I don't generally do the arrows going down is just because then I get a bunch of email questions when people are looking over their notes. Why did you do it arrow down? But we could put it, we could put it up, or we could put it down. It's definitely a choice, whichever way we want to do it. But again, the only reason I tend to put it up is because otherwise I get a lot of questions about why it was down. All right, so lithium has 3 electrons, 1, 2, and 3. And I will go ahead and let's start with this one right over here. All right, so first energy level, S block, all S's have a 0 for its M sub L, and it's going to be a -1/2. So I know I did that one kind of fast, but any questions on how we did that one? All right, so now let's do our next one. So next one is still in the first energy level, still in the S block. All S's have a 0 for their ML, and I'm going to call this one a +1/2. So any questions on how I did either of those? Okay, so I want you to try this one right here. So you're going to put it right here. So try to do the 4 quantum numbers for that 2s electron. By the way, if you don't like it going up, feel free to make it go down and then do the corresponding quantum numbers. Let's see if we can do this. All right, so it looks like Jervin is suggesting 200 +1/2. Oh, I'm sorry, Jervin has -1/2, so Andrew has +1/2. Those both work depending on which way you want to do your arrows. And it looks like Andrew's got something similar. All right, so go ahead and click in if you are done or if you'd like more time on this one. All right, excellent. And so I saw some good suggestions in the chat box there. So 2 for the second energy level, 0 because it is an s orbital, 0 because there's only one type of s orbitals, or s orbital. And then I have a plus 1/2, but you could easily have a minus 1/2 if you wanted to draw this a different way. So that will work as well. Any questions on any of these? All right, so let's try our next one. Next up, it says that we're looking at the 2p electrons in carbon. So here, I'm specifying which electrons I want to look at. So most of our elements have a lot of electrons in there, and so I usually won't ask you to do all of them. I'll usually specify which ones I want. So make sure you're looking for that in the question. So here, the 2p electrons in carbon. So if I were to do carbon's electron configuration, 1s2, 2s2, and 2p2. So it is these electrons that we care about right now. So any questions on how I got that electron configuration, or anyone want to see me get it from the periodic table? All right, so here we would have 1s, 2s, and then we always draw 3 lines when we have a p. So here's our 2p. Let me actually lower this down just a little bit here. So just for fun, I'm going to do the whole thing here. So arrow up and arrow down in the 1s, arrow up and arrow down in the 2s. Now let's take a look at the 2p. Where do you guys want to put your 2 electrons? Do you want to put them here next to each other, or do you want to be more creative and move them around somewhere else? What do you think? Anyone want to put their electrons in a more creative place? Okay, so it looks like Andrew wants them next to each other. All right, we'll go ahead and put them next to each other this time, and then next time I will give you guys the choice of where you'd like to put them, but I hear side by side from Tasso as well. All right, oops. I'm going to go ahead and put them here and here, but just be aware they don't have to be there. You could have put one over here, and you could have, let me see if I have the ability to do this. No, I was trying to spin it. Yeah. There we go. You could have it like so as well. Sorry, I'll stop playing with my devices. There we go. Okay. This is all we're looking at right now because that's all we were asked for. The 2p electrons in carbon. All right. So before we get started, I want to add something here. So remember, each of those lines represent a different type of orbital. Once upon a time, we called these px, py, and pz. But now we're going to number these. And I'm going to call this -1, 0, and +1. All right, and so let's color our electrons so we can keep track of things. All right, so that purple one that we've just done, we're going to do its quantum numbers. All right, what is the first quantum number that I'm going to put right here? Excellent. So I'm seeing a 2 from Andrew, and that is correct. So this is the second energy level. So we're putting a 2 right here. What's the next number that we need? And let me scroll up here for you to take a look. We're looking at the L. So what's the next number that we need? We're looking at the number for the L. But we want something in this right here. So remember, I see a 1 from Tasso, and that is correct. So So what we have right now is a 2p. So we need that 1 coming from the p. So let's talk about that for a moment. So this is a 2p. So the 2 goes right over here, and the p is right here. It's just that we call p P1 in that position. Any questions about why this one right here is going to be a 1 for that p? Okay. And now if we're doing this one right here, this one in purple, what's our next number? All right, excellent. I'm seeing some negative 1s come through. So this negative 1 right here goes right over here. So any questions about that negative 1 or the positive 1 that came before it? All right, so what is our last value here? All right, so it could be a minus 1/2 if you want to put it down, or we could say that it's a plus 1/2 since we have the arrow going up. But if you wanted to draw it the other way, if you wanted to draw it this way, that's perfectly valid here. I'm going to go ahead and keep it going up. All right. Questions on these numbers here that we've done so far? Let's see. Okay, so I'm hearing from a great question. And so Dravin's asking about electrons filling different boxes before pairing up. So yes, that is what we talked about before, that what we can't do is this. We can't have essentially 2 electrons in one orbital and the other one's empty. So that's why we had to spread them apart. So that is accurate. Yes. Does that answer the question, Draven?
Just one more.
Oh. I can barely hear you.
So could it also be like 1 up, 1 down, and then 1 up, but they're all in separate boxes?
Yes, it absolutely can. So it can be this and like so. And so something that's interesting is normally with no magnet, they can be in any random order, but if we apply a magnet, they will all align with the magnet. And what we can do in some of our devices, and it's something that we do actually with our NMR device, is we do a magnet that's going to flip back and forth, and when it does, these electrons will all flip with the magnet. So every time the magnet flips, those electrons flip. But if there's no magnet present, perfectly normal for some to be up and some to be down, yes. But it still follows the rule that your Chem 2 teacher taught you, that they cannot be doubled up like so. Not if you have empty orbitals. All right, so other questions on this one so far? All right, so let's try another one. Yeah, let's go with green here. All right, so now we're going to do the other electron in carbon. All right, what is the first number that we need? Excellent. So the first number is a 2. It's the second energy level. What's the second number? Excellent. So now it is a 1. And that 1 comes from the fact that P's are going to be 1s. What's our third number? Excellent. So I'm seeing lots of zeros coming through, and that is correct. We chose to put that electron here at the 0. So that's where it is. And finally, for our spin, I'm going to say plus 1/2 because mine is sitting up. If you chose to put yours down, you could call that a negative 1/2. But what do we think about our quantum numbers here, the ones that I've done in green for this electron right here that's in green? Any questions on anything so far? Okay. Just straighten up my box here. There we go. All right. Good question. So Angie's asking, do you always have to draw this right here? And the answer is no. I think it's easier to kind of connect the two, but no. If I ask you for quantum numbers, I'm only looking for something like so. And in the past, I've had people ask, well, hey, what if I did this instead and I made it a curve bracket instead of a square bracket? Would you take off points? And the answer is no. By convention, we do use a square bracket. And like I usually say, it might hurt my heart a little bit to see it another way, but I will not take off points if you do the curve instead of a square bracket or if you forget your commas. But again, quantum numbers, this is all I'm looking for. You don't need to draw this, but I find it helpful to do it, and you might as well. Okay, other questions so far? All right, so let's keep going. So next up, we're going to do one of the d electrons in cobalt. So it says just one of those d electrons, any one of the d electrons. So let's go figure out cobalt. All right, so here is cobalt. Would you all agree that cobalt is in the 3Ds because it is the 4th row, and we have a rule that says row minus 1. So cobalt is a part of the 3Ds. Excellent. So it has only asked about one of cobalt's electrons. So it doesn't say all of them, so we get to pick any one that we want. So I know that cobalt is part of the 3D. So I'm going to go ahead and draw out my d orbitals, 1, 2, 3, 4, 5, and I'm going to number them. So d's go from negative 2, negative 2, negative 1, 0, plus 1, and plus 2. And we only are going to use one electron, even though cobalt has plenty of them. Where do you guys want to put the electron? Which one of these numbers do you want to put it in? The negative 2, negative 1, 0, plus 1, plus 2? All right, so I'm hearing Maria is saying 0, and so does Tasso. So let's go ahead and put it into that 0. I don't know, aqua blue. All right, you guys want it up or down? All right, so I'm seeing down and up, but Angie typed the fastest, so let's go ahead and do it down like so. I'm hoping this aqua blue is dark enough for everybody to see. Thanks for changing to agree with Angie Tasso. All right. I'm worried that this blue isn't going to be dark enough for some of your screens, so let me actually change that up. Let's do, I don't know, dark purple. There we go. All right, so we are in the 3Ds. So what is our very first number here? Excellent, so I'm seeing 3s, yes. So the 3, and that 3 comes from the fact that we are in the 3Ds. All right, so next up, we need the number that corresponds to D. So let's go back. So what is the number for L that will correspond to D's? Excellent. So we're looking at this number right over here. Any questions on why we're going to use this number 2 here to designate our L's? Let's see. So Clinton, what you're doing is you are doing a 4s electron. So it is true that cobalt has a 4s electron. So it is true that inside of cobalt somewhere is a 4s electron. And it is also true that it would be 4, 0, 0, and you could do a positive 1/2. However, you got to be careful with the problem because this problem specifically asks for the d electron. So even though this one is present inside of cobalt, that wouldn't correctly answer this question. Oh, no worries, no worries. Those are good questions. Never be afraid. Don't be afraid to ask questions, you guys. If you have the questions, somebody else does as well, and they're not as brave and as strong as you are. All right. Other questions so far? There we go. All right. So we said this one right here would be a 2, and that 2 is because we have a d orbital. So any questions about why the second number will be a 2? All right. Then we chose to put that electron in 0. That is the specific d orbital. Oops. Therefore, that's our next number. And then, yes, I see negative 1/2 right over here. We chose to put it upside down, like so. All right, any questions on what we've done here? Aww. Oops. Okay. Any questions on what we've done here? Yes, so Jervin's asking, hey, could we do anything else for that orbital? And yes, you might say, hey, I'm not a 0 kind of person. That's just not the way I want to live my life. You could have put it over here. If you did, then this would be a 2 plus 1/2, like so. But yes, Jervin, you're right. You could put this in, oops. You could put this in any one of these. And if you would like, and if I can get this to go, there we go. You could spin it upside down or turn it right side up. All right, other questions so far? All right, so we are almost done with this. The last one is going to be one of the F electrons in europium. All right, so let's take a look at europium. Way down here. All right, so once upon a time, I told you the easiest way to remember the F's is just remember that this is a 4F and this is a 5F. If you decided not to do that, you would have to realize 58 follows 57, and then you go to 6, and then the rule is rho minus 2. And for me, that's a lot of work. I would rather just remember 4F and 5F. The one on top are the 4s, the ones on the bottom are the 5s. So for me, that's the easiest. So here's our europium, and it is a member of the 4Fs. And we get to choose one of those electrons, any one we want. So this is going to be very similar to last time. So let's give this a try. So how many lines should I draw out for the F's? We had 3 for the P's, 5 for the D's. How many do we have for the F's? Excellent. So I'm seeing 7s. Perfect. If you're ever unsure, we have twice as many elements because we can always get 2 electrons in an orbital. So if you count across the F's, there are 14. That means we need 7 orbitals because 2 electrons per orbital. All right, so 1, 2, 3, 4, 5, 6, 7. And here we're doing -3, -2, -1, 0, +1, +2, and +3. All right, so let's start off with the number. Where do you want to put that electron? Which one of those numbers should get the magical electron? All right, so I'm hearing Maria say 2, so let's go ahead and put it in 2. It's going to be right in here. Tasso, you didn't get your... Tasso, you choose whether you want it to go up or down this time. What do you think, Tasso? Up, okay. So that's where we're going to put our electron. Is everybody okay with where we chose to put our electron? All right. So now I want you all to take a moment, and you have 4 quantum numbers to put in here. These are the 4 F's. This is where we've chosen to put our electrons. And just to help you out, let me squeeze back up here for a moment. And I'm going to copy this down so you have it to look at while you're working. All right, so go ahead and give this a try. So you're filling in those 4 quantum numbers. When you get an answer, feel free to type it into the chat box. All right, so I hear Andrew saying 4, 3, 2, plus 1/2. What do y'all think of that one? All right, so it looks like we've got lots of agreement. All right. And Jervin, it's fine if you want to use 0. That's where you want to put your electron. And it's fine if you want to do it arrow down as well. All right, so go ahead and click in if you're ready to go over it or if you'd like more time. All right, so it sounds like most of you are ready, except for our mystery person who may have left their computer. Okay. All right, so I'm seeing 4 to start with, and that is correct. It comes from the 4 right over here. And then the next number I'm seeing is 3, and 3 is correct. So 3 is coming from the F's right down here. Let me go ahead and highlight these in case you want to come back later. All right, and the next number I am seeing, most of you had 2. Some of you chose a different number, and it's perfectly fine if you want to choose another number. And then I'm seeing plus 1/2 for most of you. If you chose to put your arrow going down, that's perfectly fine. You could have a minus 1/2 as well. Okay. All right, so questions on anything that we've done here with our quantum numbers? All right, so I know last time I asked, some of you said, it's okay. Is it feeling any better now to do the quantum numbers? All right, excellent. All right, so quantum numbers are really important to us. And by really important, I'm going to tell you, oh, excellent, it's getting better. So I'm going to tell you have a 100% chance of seeing them on your next exam. So if you have any trouble with them, please let me know. But also know that a lot of people find these really, really tough. So if you are struggling with them, you are in good company. And I am more than happy to help you out with them. I want to do one more question about the quantum numbers. And it says, which of the following quantum numbers cannot exist? So I want you to give this a try. And my recommendation would be try to either come up with its orbital diagram or its electron configuration based on this. Try to figure out where is that electron and is that a real location. So for instance, if it said that you had an electron in the 1f, you know there's no such thing as a 1f, so that one can't exist. So think about this A, B, C, D, and E. It's telling you where an electron is. Which of these is giving you a location that cannot exist? So give this a try. All right, so we have one vote for C already. And now we have a vote for B coming through. And now we've got a vote for C as well. So it looks like we're getting votes for C and B. We got more votes for C coming through. All right, so go ahead and click in if you'd like more time or if you're ready to go over it. All right, looks like we got a couple people who want some more time, so let's go ahead and take a minute or two. Looks like C is quite the popular letter right now, but I've also seen some B's. All right, so let's go ahead and give this one a shot. Before we do, I want to bring down this right here, because this often trips people up. Put that off to the side. All right, so let's go ahead and look at the first one. So the first one says that it is in the second energy level, and it is a p orbital. And then it says it is in the -1 location, and it is an arrow up. So can A exist? Yes. Excellent. All right, so now let's look at B. So B says it's in the third energy level. It is a 2, so that means it's a D. And so here we have 1, 2, 3, 4, 5. -2, -1, 0, +1, and +2. So it says it's in position 0, and it is -1/2. Can that exist? Excellent. All right. Make these just a little smaller. All right, so now let's try that C that everybody's been typing about. Third energy level. And the next number is 3, which indicates an F. Is there such thing as a 3F? Excellent. There are no 3Fs. So just to go back to those Fs, we only have a 4 and 5F. There are no 3Fs. So C is our answer because the 3F doesn't exist. But let's go ahead and do the D just for fun. So fourth energy level, and then there's a 3 in there, and our 3 is an F. So this is a 4F. And now I'm going to do 7 lines, 1, 2, 3, 4, 5, 6, 7. And for F's, -3, -2, -1, 0, +1, +2, and +3. We're on location 0, and it is a +1/2 like so. All right, so D does exist as well. So it is C that doesn't exist. Sorry about that, my screen was stuck for a moment. All right, any questions on how we did this? All right, so students often ask me, well, how are you going to test me on quantum numbers? So it is always possible that I could ask you something like this. So write out the quantum numbers for one of the D electrons in cobalt. But it's also possible for me to give you a list and say either which one does exist or which one does not exist. So any questions on how we're doing this one? All right, so next class during lecture, we will start in here with the periodic properties, but I want to switch over to lab. So do you guys want a 5-minute break or a 10-minute break? We're not going to spend too long on the lab today. All right, so I hear a lot of 5s coming through. Okay. You guys are eager to get on to do more chemistry at home. That's how I'd like to see it. All right, so let's go ahead and meet back up at 8 o'clock. So we're going to take a 5-minute break, and then we will talk about our lab, and our lab today is lab 7. I'm going to go ahead and pause or stop our video.